Last time, we tried to re-express the Hamiltonian of a Coulomb interacting electron gas in terms of the density of electron, or density operator, rho, in K space, where rho of Q is given by particle-Hall pair-like operator. And from now on, we should start from this Hamiltonian, and we will show step by step that this Hamiltonian, if we treat this Hamiltonian quantum mechanically by studying the Heisenberg equation motion for the density operator, rho of Q, and we will derive this plasma oscillations of electron densities in solids, especially in metals, which has been observed for decades, right? So this is a very important phenomena of a Coulomb interactions in metals, where electrons can actually dance together in a particular frequency called plasma oscillation frequency, and we will derive such plasma oscillations based on this Hamiltonian. And next, we will demonstrate that this Hamiltonian would also give rise to the screening of a Coulomb interaction. Okay, namely, the Thomas Fermi results that the Coulomb interaction is not long range anymore. It is cut off by the screening effect. And we will derive such a Coulomb screening effect purely quantum mechanically. Okay, so without the help of the classical mechanics, and then this is the correct starting point. The density operator for electron in Q space is given by this kind of a particle-Hall pair excitation, and we will start from here, and we try to study this kind of elementary excitations. Okay, and there are two different kinds of elementary excitations. One is the very large momentum transfer, energy transfer, which is the single particle-Hall excitation. Another type of the particle excitations are so-called the plasma oscillations, and it is the collective oscillation. Okay, so it is very low momentum transfer or long wavelengths limit of the electron-hole pair excitations, and very close to the Fermi surface, and it involves everybody. Okay, so all the electrons get involved in this plasma oscillations, and we will differentiate the single particle-Hall pair excitations from the collective plasma oscillations. Okay, so by studying the equation motion for this density operator based on this Hamiltonian. Okay, so this is what we should do. So let's just study first this particle-Hall excitations or electron-Hall excitations. So we could ask whether this kind of single particle excitation is actually, we should derive such an operator which leads to such a single particle excitation and the eigenstate of such a single particle Hall pair. Okay, so we should introduce an operator called B dagger, which creates an excitation, presumably electron-Hall excitations in a many-body system in the ground state, which we call psi. Remember, psi is the eigenstate of the Hamiltonian without the electron-Hall pair excitation. So suppose the eigenstate of the Hamiltonian is known, and the eigenenergy is given by epsilon 0, and we would like to create such a electron-Hall pair excitations by applying such a B dagger operator onto the ground state, and we create such a excitation. And we would like to find out this energy or eigenenergy of such a excited state, and assume that the epsilon b is the energy that requires to have such a excitation, and this kind of excited state can also satisfy this eigenvalue equation, meaning this state is also the eigenstate of Hamiltonian. So this is just assumption that we assume such excited state exists, and the excited state also is the eigenstate of the Hamiltonian, but with the eigenenergy epsilon b additional to the ground state energy epsilon 0. And we would like to find out what this B dagger is. So this is our question, and this is what we would like to show or prove what kind of operator B dagger can do the job. And so let me just rearrange this eigenvalue equation of this 2. And if I rearrange this term, I could get this type of commutator between H and B dagger acting on the psi is given by this extra excited state energy epsilon b as an eigenvalue multiplied by this excited state B dagger acting on psi. And if I rearrange this, this is the commutator between the Hamiltonian and the B dagger is given by epsilon b and B dagger. Okay, so this is the equation that leads to such a excited state, right? So the question is, what is B dagger? Of course, the B dagger is closely related to the density operator rho of Q, but not quite. Okay, because you can see that this rho of Q is given by summing over all such kind of electron hole pair with the momentum K and K minus Q. But this B dagger should describe such a single particle hole pair excitation or the many single particle hole excitation. So that is the question. So we guess, suppose B dagger describes a single particle hole excitation, and with that form, and we want to check whether this B dagger really plays a role as the creation of a single particle excitation, and yet after you create such an excitation, this excited state is also the eigenstate of the Hamiltonian. Okay, so we want to check whether this operator C dagger P plus Q CP can do the job. Okay, so it is just a very straightforward guess, okay, because you destroyed a single electron below the Fermi surface and then create another one above the Fermi surface with K plus or minus Q, and such an operator looks like the one that we are looking for. Okay, of course our naive expectation is not completely correct because of the Hamiltonian. It's non-trivial, but let's check whether we could really identify this B dagger as the C dagger P plus QCP, as we could naively expect. Okay, so if this is not the answer, and under what conditions can this identification be reasonable? Okay, so because this is our naive intuition and expectation that B dagger should be related to that operator, but we'll see later that this is not exactly correct. Okay, but we can make some approximation that maybe we could, roughly speaking, identify this. So let's check. So the way that we check this, of course, is to check the commutator, because we want to check that this equation is satisfied. Suppose B dagger is simply just C dagger P plus QCP, and we simply just plug in this equation and see if this equation is satisfied. Okay, so let's do the job. Suppose this is our B dagger operator, and we could calculate this commutator between the Hamiltonian. Remember, the Hamiltonian is given by this red box over there, and we need to evaluate this commutator. And after some calculation, which I assigned this to you as a homework exercise, you can show that this is given by these two terms. Okay, so this becomes your homework problem. Okay, derive it. Okay, so starting from the commutator between H and this operator, and you plug in this Hamiltonian over there, and taking advantage of this anti-commutation rules between this Fermi operator, and you are able to show that this is indeed the case, that the commutator is equal to this a bit complicated terms right there. Okay, and additionally, you could also verify that the second term looks horrible, right? Very complicated, but you could look at this symmetry between, say, P and Q and so on. Okay, so you can look at this symmetry, right? And you will show that the second term vanishes altogether. Okay, so this term vanishes. Again, this is another homework. So the first homework is to derive such two terms, and the second homework is to show the second term vanishes. Okay, so the way that you show the second term vanishes is to take advantage of the symmetry between these indices P and Q, and also this term, the second term, is actually not identically 0, but very, very small. Okay, so I should say the second term is actually very, very small if this epsilon P plus Q minus epsilon P is actually very large. Okay, so you can show that the second term indeed is very, very small compared to the first term if this energy difference is actually very large. Okay, so let's take a short break. When we come back, we will continue analyzing this term. Okay, so as I mentioned over here, the second term does not automatically vanish, okay, but under some conditions. The conditions is that when the energy difference between this P plus Q state and state P is very, very large, and this first term dominates over the second term. Okay, so therefore you could argue and show that the second term approaches 0 compared to the first term, or the second term could be neglected. All right, so so you are able to show this maybe after we introduce this concept of the random phase approximation, or this Fourier component of the electron density operator. But in any case, you can see that there, in the bracket, you have this difference between this C dagger C and C dagger C with different momentum indices, and under the assumption that the Q is very large and this epsilon P plus Q is much greater than epsilon P, or large momentum transfer limit, and the first term, the kinetic energy term, actually dominated over the Coulomb term. So the second term could be neglected. So precisely this statement here. So if we are considering a very high energy single particle Hall excitations, and this type of approximation could be reasonable. Okay, so in other words, suppose I excite this inner shell state, and I excite the state by a very large momentum transfer Q, and then this excited state electron carry a large momentum P plus Q, and with very, very large momentum transfer Q, so that this epsilon P plus Q is much larger than the epsilon P. So in such a high energy and large momentum transfer limit, and we can forget about the second term and approximately identify this commutator as the same as the kinetic energy difference multiplied by the operator again. Okay, so this is approximately the equation that we're looking for, because this is our initial guess, right? Suppose this B dagger can create such a single particle hole excitation, and after creating such a single particle hole excitation, and this excited state could still be the eigenstate of the Hamiltonian. Okay, so you can see that this is not automatically true because there's a second term. Okay, suppose we neglect the second term and we look at only the first term, and the first term is precisely what we are looking for, right? Because the eigenenergy of the first term is precisely given by epsilon b, right? Epsilon b is the energy difference between these two states, right? And suppose we have no second term over there, only the first term, and then we're done. Okay? So the B dagger with such an initial guess is a good approximation if we are talking about a very large momentum transfer excitation. Okay? Good. So therefore, we successfully identify such a B dagger operator as the single electron hole pair excitation in this Coulomb interacting electron gas. Okay? But under such assumption that momentum transfer to be very, very large. Okay? But for small momentum transfer limit, if Q is small, then this is not a good approximation. Okay? So then we cannot neglect the second term. Let me just mark this is the second term, this is the first term. Okay? And therefore, in the small momentum limit, small momentum transfer limit, this B dagger is not going to be the C dagger P plus QCP, but something else. However, there's a hint. The hint is given by this kind of identity that suppose I sum over P and also Q prime of the second term, term 2. And by the symmetry argument, I can show that this automatically vanishes, identically exact. Okay, so what it means is that if I do not sum over this P, but only sum over Q prime, this term cannot be 0 automatically. However, if I sum over both P and Q prime for the second term, I can show explicitly that this term identically vanishes. This is a third homework. You can show by interchanging the indices P and P prime or shifts P and P prime by the amount of Q or minus Q, and you could show explicitly that these two brackets automatically vanishes if you sum over both P and Q prime because of the minus sign. Okay, so this term cancels that term, this term cancels that term, but it is your job to show that this this small bracket here and there, when you sum over both P and Q prime, vanishes. Okay, so this indicates that maybe we need really to sum over all such momentum state P in order to find out the electron hole pair excitation and the corresponding operator. And this hint really leads to such a calculation that this density operator may do the job. So remember, the density operator, rho of Q, is such a combination of C dagger P plus QCP with a summation over all possible momentum P. So this looks very similar to such a summation over here that if you sum over all possible single particle hole excitation, and you may end up finding the correct operator corresponding to such excitation which involve all the electron state P, right? So such a operator should be related to rho. Okay, so this is the hint, very important hint, that if you study the equation motion for the rho of Q or the commutator between H and rho of Q, and you may be able to find that this electron hole pair excitation, when you sum over all possible electron state within the Fermi surface, and this operator, which generates such many electron hole pair excitations, is directly related to the rho operator. So this indicates that this operator, whatever this operator, which I call this A, which generates many single electron hole pair excitation, should be the function of rho of Q. And whether this is exactly rho of Q, so we'll see. So this is the many-body problem that when you consider this electron hole pair excitations for such a Coulomb interacting electron gas, you no longer consider only a single electron hole pair excitation. Instead, you should think about all the possible single electron hole pair excitation simultaneously, okay? Because that's what it happens. And that's why if you consider only a single electron hole pair excitation, and this excited state is the eigenstate of the Hamiltonian only in such a large momentum transfer limit. So if you consider the small momentum transfer, which is the low energy and long wavelengths or low temperature limits, and such excitations must involve everybody. So this important hint tells us that the low energy and low momentum transfer limit excitations must involve everybody. Everybody, I mean all electrons. Okay, so that's the essence of plasma oscillation or the density fluctuations. Okay, so this is a many-body phenomena that involves all electrons within the Fermi surface. Okay, so this is a many-body phenomena that involves all electrons within the Fermi surface in the form of this density operator rho for a small momentum transfer limit. Okay, so this is our next job, is to evaluate this equation motion for this electron density operator to actually create such a low energy or low temperature, low momentum transfer limit excitations, and which could describe such electron density fluctuations in time. This is a simple exercise that tells us a very important physics, namely, if you would like to describe such a low energy excitations of electron hole pair, then you must consider all the electrons that dance together. Okay, so let's take a short break. When we come back, we will try to evaluate this, say, Heisenberg equation motion for this electron density operator from standard quantum mechanics. So let me just summarize what we have learned. Okay, so we learned that in a high energy, large momentum transfer limit, this B-Deg operator creates a single particle hole excitation. But if you consider the low energy or low temperature excitations, which is what we're interested in because we are interested in the low temperature properties of solids. So at low temperatures, such excitations involve only a small momentum transfer, not large momentum transfer. Because at low temperatures, the excitations cannot be that high energy, of course, right? So in such an interesting regime, electrons actually dance together. Okay, so we cannot consider a single particle excitation, but we should consider electron excitations that involve all electrons. So this is the lesson, and therefore we should look at this equation of motion for the electron density, and we should study how this density of electrons fluctuates in time, and also how this electron density that dance together. So this is the essence of this physics. So let's look at this equation motion. Remember from quantum mechanics, so we could construct the Heisenberg operator, right? Okay, from the Schrödinger picture, and we could either consider the time evolution of a Schrödinger state or the time evolution of the Heisenberg operator. So either way. But it is more convenient here to consider the Heisenberg operator, meaning the operator which depends on time, okay, rather than the quantum state or Schrödinger state. Okay, so in quantum mechanics, you know very well that if you consider time evolution of the Heisenberg operator, and you must solve this equation motion, which we call this Heisenberg equation motion. So let's check the equation motion for the density operator, because we highly suspect that this operator, the correct B dagger, is actually rho, or rho dagger, which creates electron hole pair excitations, many electron hole pair excitations. Okay? But we need to check. The way that we check is precisely by solving the Heisenberg equation motion. You know very well that suppose we can find such a section of a Heisenberg equation motion, and then we're done. Because then we know that this operator B dagger is indeed this rho dagger of Q, and we also could actually get such a density fluctuation frequencies, and which involve all the electron states. But things are not that simple as always, because let me just write down this equation motion for rho dagger of Q. Suppose that everything works very well, then ideally I will get h bar omega rho dagger of Q, and this omega is the oscillation frequency, and because you could consider this is the time evolution of your Heisenberg operator, right? Suppose I have such a initial ansatz for the time evolution of the Heisenberg operator for rho of Q or rho dagger of Q, and I plug in here, and I could just evaluate such a commutator between the Hamiltonian and rho dagger of Q, and everything goes well, and ideally we will derive such a h bar omega rho dagger of Q on the right hand side, with the omega is related to the commutator between h and rho dagger of Q. Suppose I evaluate this commutator, I get something, and that something under such a initial ansatz or initial guess should be identified as the oscillation frequency for such a rho dagger of Q. And then we're done. Okay? So then we could really identify such a frequency which is related to the commutator. It's a function of a commutator. Okay? When you finish this commutator calculation, and you will find that this is a function of, say, the Coulomb potential, and so on and so forth. V of Q and mass and h bar, or whatever. Okay? So we will derive such a frequency in just a moment. So up to here, it's all right. It's just your quantum mechanics, nothing more. So let's just really do the job. Suppose I compute this commutator between the Hamiltonian and rho dagger of Q. What I get, remember, is this sum over P and epsilon P plus Q minus epsilon P, C dagger P plus Q, and Cp, and plus sum over P, the second term, right? Okay, so the difference between this commutator and the previous commutator is whether we sum over P or not. So the previous calculation, the single electron hole pair excitation. So remember previously when we calculate this B operator as C dagger P plus Q, see P as a single electron hole pair excitation operator, and then we did not sum over P, right? Remember that it's just a single operator, and we just erase this. So this is given by the first term and the second term. Okay, so now we are doing almost exactly the same calculation, except we sum over P, because this is what we should do, right? This is the row dagger of Q. Remember that. So the difference between this single particle excitation operator and row dagger of Q is the summation over P. Okay, so the first operator does not sum over P, but the second operator does sum over P. And whether there's a summation over P matters, because, of course, the first single particle hole pair excitation operator just, by definition, described just a single electron hole pair excitation. Okay, involves only one electron state. Okay, but the second operation, which involves the sum of all possible electron states, which involves everybody. So this is a very important point. Let me just emphasize this. So the second operation involves all electron, but the first operation involves only single electron. Okay, so that's the difference. Okay, so and we highly suspect that the second operation will work. So we could show very clearly that this is given by sum over P, the first term, but you know that when you sum over P for the second term, this vanishes, right? This vanishes. And so we exactly derive such identity. So this identity, without any approximation, holds. However, this is not what we want. Why? Because this is given by sum over P, this energy difference, multiplied by this operator, right? But this is not the same as this one with epsilon B. So now you see the difference. The difference still lies the summation over P, because this summation over P involves the state P in this first energy difference term, and also involves the operator C dagger P plus QCP. So it involves all the states. But the bottom line is what we want. We want some constant eigenenergy, right, multiplied by the operator itself, right? But remember, the bottom line is the summation over P, which involves only the electron operator C dagger and C, which does not involve the kinetic energy epsilon. And therefore, we cannot simply just move the summation inside here and say that they are the same. No, they are not the same. They are not the same. Okay, so this is the trouble, that when we evaluate the Heisenberg equation motion for row dagger of Q, we cannot get back to the right-hand side that we really want. No, this is not equal to the constant h bar omega times the density operator row dagger of Q. This is very similar to that term, but not exactly the same. Okay, it's very different because the summing over P involves everyone. Okay, so we cannot extract the prefactor as a constant multiplied by the row dagger of Q. Sorry, they are not the same. So it seems that we have some trouble. So let's take a short break. When we come back, we will, again, based on this observation and trouble, we could make progress. Let's continue. So previously, we showed that if we suspect that this B dagger operator, which creates the electron hole pair excitations, including interacting electron gas, and we should prove that this satisfies Heisenberg equation motion, and then we could get the oscillation frequency omega by calculating this commutator between H and row dagger. However, we just realized that if we do this calculation, and the right-hand side of the equation cannot be simply just a constant eigenvalue H bar omega times this row dagger of Q, because of the summation over P involves all the terms over here. And therefore, we cannot directly get things down and find out what this oscillation frequency is. However, there's a solution. So if this, this first order time derivative of the Heisenberg equation motion doesn't work, we may try to evaluate this Heisenberg equation motion up to second order in time derivative. So the first order equation motion does not succeed, and why not try the second order derivative? Okay, so in other words, so let's just keep a hope at the second order in time derivative of the Heisenberg equation motion. Namely, if I simply take the second time derivative of this Rho-Dagger operator, and by applying the Heisenberg equation motion second time, and on the right-hand side, it should be a double commutator, right? It's a commutator of a commutator. So I believe that most of you already encountered such a double commutator in quantum mechanics. Okay, so this is not totally stranger to you, and so we simply just keep one more time derivative of this Rho-Dagger, and then we try to evaluate this double commutator, and hopefully, if we are lucky, and we can show that on the right-hand side, it can be simplified as a constant prefactor, h bar square omega square, as an eigenvalue, and multiplied by the Rho-Dagger operator. Hopefully, that's cross our fingers, and of course it will work. Otherwise, I will not introduce this calculation, right? But how exactly this calculation done is our job next. Okay, so whether this is the exactly identical between the two sides or approximation. So if this is not identically equivalent between the two, and under what conditions that we could approximately identify these two. So of course the answer is the approximation. So this would not be the exact identity, but under a reasonable approximation, we could approximately consider the right-hand side as the constant times the Rho-Dagger of Q once we evaluate the second time derivative of Rho-Dagger of Q. All right? Okay, so I think the logic is very clear. So let's do the messy job. But we already did this first time derivative, or this first commutator. So we plug in this, the commutator inside the commutator, and we end up by doing this commutator between the Hamiltonian and the result of the first commutator. Okay? Because the second term already vanishes by summing over P. So this will be your homework. Unfortunately and fortunately, please derive that the second commutator equals this complicated form. Okay? So by the way, you could look at this kind of commutator or double commutator calculation by reading the David Pine's lecture notes, the elementary excitation solids, and also from Kittel's second book, Quantum Theory of Solids. Okay, so these two references are really useful when you try to evaluate, the single and double commutator. The only weapon you have is the anti-commutation relations between the Fermi operators. That's all. Okay, the remaining job is just to rearrange all this term and simplify this full operator, and then try to combine some of the operators into this Rho-Dagger form. Okay, so that's your job. And pull out these common factors as this small bracket here. You simply just do this all the time and combine this and that, and you may need to shift this momentum indices so that this term, that could be combined. Okay, this is technical points that you need to conquer. So let's just continue. Suppose I label the first term, again, term 1, and the second term, term 2. Okay, so then I could further simplify these two terms. So let's just look at the first term. The first term is given by this, and let's just expand this kinetic energy epsilon p for a free electron, and take the difference between these two energies at different momentums. And this becomes 2p dot q. Remember, both p and q are vectors, right? So they're momentum vectors. So you could just cancel this p squared term, right? If you simply just take the difference, and the p squared term is the common term, which will be canceled out, but you get the cross term p dot q and q dot p, which is the same 2 times p dot q, and also the q squared term. Okay, but you need to square this. So this is just a difference in energy, but you need to square this energy difference, because the reason is we have the square is because we are evaluating a double commutator. A single commutator will lead to such an energy difference, and a double commutator is a square of the single commutator result, right? Okay, so you get a square of the energy differences. And we need to square this. And of course, need to square this. And then C delta P plus Q and Cp. And we can further make some approximations. And we know that this momentum P should be very close to the Fermi surface. So we could approximately write this term h bar squared P dot Q as h bar squared Fermi velocity dotted Q, right? Of course. Right, because P is actually very close to the Kf, and P over m is actually Kf over m. So this momentum divided by the mass is the Fermi velocity, right? So we could just make such approximation. And another approximation is that the momentum transfer is actually very, very small. But how small this, we will just see in just a moment. And under such assumption, the square of the energy difference now is actually given approximately by this h bar power 4 Vf square and q square. Since the momentum transfer is actually very, very small, and therefore we forget about this q square term. Q square term is actually much less than 2p dot q. Okay, so we forget about this q square, because remember this low momentum transfer and long wavelength limit corresponds to the low temperature excitations. Okay, so in solid state, we are always interested in the low temperature behavior, because in the high temperature limit, things will recover. I'll go back to the classical mechanics. The quantum phenomena occurs only at a very, very low temperature, where the excited state energies are really, really low. Therefore, we need to look at this regime where the momentum transfer is very, very low. And as a result, we can just neglect this second term, because this is very, very small compared to the first term. And the first term can be further approximately written as this Fermi velocity dotted the momentum transfer q. And as a result, if you square this term, this will be this h bar to the 4th times square of the Fermi velocity times q square. Okay, so here comes the assumption, the further assumption. So we'll assume further that this term is actually much smaller than this h bar square omega square. So I put this subscript p refers to the plasma oscillation frequency, which we will derive later. But suppose there is such omega p here. So remember, this right-hand side is given by h bar square omega square. And because q square is really, really small, so we can further consider that, assume that suppose this term h bar to the power 4th Vf square times q square is actually much smaller compared to this h bar squared omega p squared. But whether this assumption holds need to be verified. Okay, so we will check whether this assumption is a reasonable assumption. Let's check later. First, let's just make such assumption, and therefore this term is actually much less than h bar squared omega p squared, and therefore we could totally neglect such term. Okay, but there's a big if that we need to verify indeed when we derive such omega p, which is a function of the electron density and mass and and things like that. Okay, so once we derive the value of omega p, we could go back and check whether this condition is satisfied. But at the moment, let's just forget about this first term, because this is simply proportional to the at least q squared, and q is very, very small, and in such a small q limit, we could forget about this term. And of course, if you do not forget about this term, and you would not recover such a simple and elegant result on the right-hand side. And this assumption is the origin of the approximation. So we make such approximation that the first term, approximately 0, okay? And we will focus on the remaining, the second term, the complicated term. And later, when we deal with the second term, and we can simplify the second term, and then we will show that this term can be written in terms of such a constant times rho deg of q. So let's take a short break. Sorry, there are a bit too many homeworks assignment today, but this is a very good exercise for you to really get familiarized with this commutation relation. So remember, our goal is to use the second quantization formalism to study solid state physics, but again, using quantum mechanics. Okay, so it is not a single particle quantum mechanics. Instead, it is the many body quantum mechanics. So consider this is just a generalization of your quantum mechanics course to many electron states, right? And there are many ions and electrons. They are interacting by Coulomb, and try to use quantum mechanics. So this is, what this course is really about. And once again, so you need to use the quantum mechanics all the time. And therefore, this commutation and anti-commutation relations are really, really important when you second quantize the everything. And therefore, the homework exercises are important. So this is my justification why I assign many homeworks today. Even if you are doing experiments, if you are experimentalist, and at least once in your lifetime, you could do this algebra by yourself. And once you're done, you can forget about how you derive those equations, but at least you convince yourself that I can understand this physics. If you are doing theories, and there's no excuse that you can avoid such a exercise. Even if you are doing high energy theory, and these calculations are really useful. And the conclusion is that at least you need to do such a homework exercise once in your lifetime. And you may forget about those after you accomplish this exercise. But don't forget too soon. So, and we will focus on the second term. But before we look at the second term, there's a very important approximation which we will use here now and also later to derive the Coulomb screening, and this approximation called the random phase approximation. So you may have heard about this name, RPA, in the book, and let's formally introduce such approximation. So this is a very useful approximation to study low temperature behaviors of metals and all other electronic states, materials. So remember, we consider the density profile as a function of the position, and we made such an assumption earlier by saying that the on average, the electron density is a constant, okay, but plus minus some small deviation or small fluctuations which lead to this density variations, and such a profile is just an assumption. So who says that the density of electrons should look like this? What about the other very large and very random rapid fluctuation? What about this? So why not consider such a very rapidly varying, rapidly changing density profile in metals? Of course, this is a possibility, but in reality, we could approximately consider the electron density in, say, at least in metals does not look like this. Okay, look more like this, and therefore this is the a realistic assumption, but we need to justify this assumption. So the justification is this. So let me just introduce this random phase approximation. So the definition of this random phase approximation is again given by this Fourier decomposition of the density profile in K space or in momentum space. So we consider the variations in electron density over space is a small perturbation, or it's a very small variation compared to the average electron density n0 as a constant. Okay, so this is our assumption, but officially this assumption needs to be justified, and for historical reasons, people call this assumption the random phase approximation. The reason why we call this random phase, what is random about? Okay, which quantity is random? Okay, so let me explain. Okay, so suppose this, the Fourier decomposition of the electron density variable over space is given by such a Fourier sum, and this approximation that we just mentioned just says that the Q equals 0 component, remember this Q equals 0 component corresponds to the average electron density, right? Okay, we already proved that many times. Okay, if Q equals 0, you simply sum over all the electron density and divide it by this volume, which is the average electron density. So rho 0 is much greater than the other term, finite Q component. So this approximation says that the RPA assumption says that rho 0 component is actually much larger than the finite Q component of the density of electron. So in other words, this assumption actually is official formulation for that picture or that graph that I just sketched here, that the small fluctuations here, the amplitude of that small fluctuation is really small compared to the average electron density. Okay, so this is the RPA, but what is random about? Well, remember, the small density variation, which is the finite Q component of the rho, carry a phase, right? Okay, and this phase e to the iq dot r, this q dot r phase is actually random. Why? Because you sum over all possible q non-zero, and q is arbitrary, and therefore we call this random. So I don't think this is a really good name, but historically people just called this phase the random phase, and this approximation the random phase approximation. So in essence, what we really assume is that the average electron density is much greater than the small variation in density. Okay, so let's just maybe do some very little exercise to actually justify that this variation in the amplitude of the density fluctuations is really small, and which is consistent with our assumption here. Suppose I consider a single wavelength fluctuations of electron density, and this just plotted here, and which ends somewhere here. Okay, just a single period of oscillation in density, and suppose that the single period ends at 2 pi, and this lambda is given by this length of this from here to here, and the amplitude between the maximum and minimum value of this variation is given by A, and we can show that the amplitude of the oscillation is actually small, and by this RPA assumption. Okay, so let's just do the simple algebra. With rho Q equals to 2 pi over L corresponds to such density fluctuations, because this momentum Q is given by this phase 2 pi over L, and lambda is given by L, and therefore this Q value is the correct value for such a density profile. And let's compute this amplitude A, which is proportional to the rho when Q equals 2 pi over L. So let's just do the algebra. E to the minus I 2 pi over L dotted x, rho of x dx. And you can very easily just use this rho of x profile given in this plot, and you plug in here, and you could just evaluate this. Suppose theta 2 pi over L times x, and this is given by this integral, the theta of cosine theta times rho 0 plus A times sine theta. Okay, so when you finish this sine cosine evaluation, you find this is given by precisely the A. Okay, so indeed this rho of Q, when Q is particular value 2 pi over L, is actually given by the amplitude of that fluctuation. And this actually agrees with our assumption that a finite Q component of the density of electrons is actually much smaller than rho 0, because this is our assumption, right? So this is much less than rho of 0. So this agrees, this is consistent with the RPA. So therefore, again, based on this simple check, we know that if we simply just make such approximation, and this is really telling us that the amplitude fluctuations of this rho is actually corresponds to the finite Q component of this density, and which is much smaller than its average electron density. So we will take advantage of such a RPA when we evaluate the second term, and under RPA we only need to keep the leading order term, which is proportional to rho 0. Remember that, okay? So remember, we have some term like this, rho dagger with some momentum P plus Q or something, m times rho in the second term. But when we sum over P or Q or whatever, at the end of the day, we should take advantage of such a random phase approximation, and we'll show later that this is actually up to leading order is given by the average density rho 0 multiplied by a small finite Q component of the rho density operator. And we forget about all the rho Q term, which is higher order under such RPA. So we keep only up to the leading order term. So of course we may end up with some rho 0 squared, but let's just look at this more carefully. Okay, so let's just compute the second term. So let me just repeat the second term. 2 times sum over P and Q prime bar square of Q divided by M V Q prime divided by 2, and this complicated term. So let's just simplify. So sum over P and Q prime. Okay, so you could take advantage of the definition of this density operator in Q space and reorganize the C diagram C by properly shifting the momentum P and Q prime and so on, and you could show that the second term is the same as this term without any approximation. So let's just continue. And remember that this rho dagger of Q is actually rho minus Q. So this term is actually rho of Q prime. So I can just redefine my indices P and Q prime and so on. So let's try to do that. Okay, so this, suppose I just define P plus Q prime as my new momentum P prime, and P minus Q prime is actually P prime. Okay, and so this term in the brackets is given by this term. So let me just write it here, which is sum over P prime and Q prime and VQ prime. So we will see later why I'm doing this. Well, time is up, but you can look at this, the first term here, that you get rho dagger, and rho dagger, rho, right? Or rho, rho, right? So with different momentum here, and in particular, if you look at this term, rho dagger Q prime minus Q, and rho of Q prime dagger. So by an RPA, you could immediately see that if Q prime is Q, and the first rho dagger becomes rho dagger of 0, right? Which is the leading order. And you could see that if you could have such a term like rho 0, rho dagger 0, rho dagger 0, which is not possible because these momentums are different. So you cannot make Q prime 0 at the same time, Q prime minus Q 0, which means that both Q and Q prime is 0, which is not allowed. Okay, and therefore the leading order term for this rho dagger with different momentum indices is given by rho dagger 0, rho dagger Q. So which is precisely coming from this RPA assumption that rho 0 is much larger than rho of Q. Okay, so our time is up. So we will continue and finish this calculation next time. So it looks promising that if we analyze this Q and Q prime value in such a way that we only take care of the leading order term, and it is possible that we'll get a constant prefactor times rho dagger of Q, okay, after this double commutator. Great. So I will see you on next Monday.